Okay, so hello. My name is Bok Woon, and today I'll be talking about a SQL library, a SQL query builder library for Go. Okay, so who am I? I am a computer engineering student from the National University of Singapore, and I use Go for my final year project. It was a website for facilitating like student submissions for school module, and I didn't use any ORMs. I just used vanilla SQL, and in doing so, I came across multiple pain points while developing with plain SQL in Go. Right? So these are the current problems with using the Golang's official database SQL library. So it's not type safe. Everything is just a query string. And there is a lot of boilerplate when you're writing SQL. Handling nested structs and nulls is messy. And if you want to programmatically build queries, you have to build strings using the programming language. So what is type safety? Type safety in this context is about existence checks and data type checks. Existence checks is, let's say you have a table, it ensures that you don't try to invoke a non-existent column from the table. And data type checks is when it checks whether you're doing a valid operation on the data type. So for example, in this case, email is a string, you can't add one to it. And you'll notice that this is mirrored in Go, where there's also existence checks. You cannot invoke a non-existent field on a struct. And also data type checks, you can't add one to a string. So the SQL compiler, when it looks at SQL code, it's type safe. But the problem comes when you embed SQL code within Go code. And the Go compiler, it knows nothing about SQL code. It says, this is not type safe. So you basically lose all type information when you embed SQL within Go. And how we ensure type safety is by mapping our table schemas into native Go types so that we can reference them safely. So from something like this into something like this. Oh, okay. Yes. So if you guys have any questions during the demonstration, you can just drop it anytime in the chat, and then I'll pick up on it at the end of maybe each example. And this is a demonstration to get started with SQ. This is the table schema that we'll be using for the demonstration. To put it in words, basically, there will be a bunch of teams. Each team will have multiple users. And each team will be making multiple submissions for assignments that are assigned to them, all right? So this is like many users in one team. One team can make many submissions, and each submission is targeting one assignment. Okay, right. So let me just get started with it. Okay, I have already gotten this, so I don't need to do this. I'll be using Postgres. So, I'll just copy the next command. Okay, so now I'll generate this. I'll just show you what it looks like. So you can see here when I run tables, this is like the 4 tables that I've shown you previously. You just plug in the URL that you use, SSL mode equals disable. Okay, so now you see that there's a query, and then tell you like 4 tables were written into this. And let's take a look at what this result looks like. Right, so just to bring up side by side, this is what the table looks like, and this is what the generated definitions look like. So we have, I'll show you the users table, for example, right? You've got user ID here, and it generates an equivalent struct that looks like users here. Yes, so you can see it maps like one-to-one. There's a user ID here. It's a number field. This is a name. This is a string field. Team ID created that. It's a time field, so on and so forth. And then this is just the type definition. You've got a constructor here as well that actually gives each column their correct column names, as well as initializes the schema and the name of the table. Okay, so that's table there. And now let's see what is next. In example 1, I'll be talking about compile time guarantees. All right, so the benefits of SQ is that it guarantees that your columns exist. It guarantees that you use the right operations on the right columns. And it guarantees that you map the data types, your columns to the right data types. And it guarantees that you map the columns in the right order. So let's see what it looks like first without any in the vanilla SQL way, database SQL way, right? So this is the query. There is, wait, is this, I can't really see it. Yeah, I think this is big enough. Okay, yes. So this, you can just take a look at this query. There's nothing special about it, nothing surprising. So now let's take a look at what the guarantees are. Does it fulfill the guarantees? All right. So does it guarantee that your columns exist? If I mistype this, and then I run the first example, it'll tell me that it's a compile time error. Basically, user ID doesn't exist. But the thing is, it's a runtime error. Sorry, so it's not a compile time error. So does it guarantee that I use the right operations on the right columns? Let's say I've got name not equals to email. If I do this, I can't compare a name with a number in an integer. Again, it's a runtime error, right? You can't compare text with integer over here. Okay, so does it guarantee that you map the columns to the right data type? And again, you can see here, let's see, the second one, this is a name, right? If I accidentally write user ID, that's an integer, it compiles fine, but it tells me, you know, you can't stuff a string into an int, invalid syntax. Another runtime error. And does it guarantee that you map the columns in the right order? So you notice that thing about database SQL is, when you specify a order here, user ID, name, email, created at, you have to follow it exactly here, user ID, name, email, created at. If you mess up the order, let's say you mess up user email and name, you won't even get a runtime error. Everything runs fine. It's just that now you've got your name is the email and your email is the name. That's like even worse than a runtime error. It's like a logic error. And let's see now what the equivalent SQL query looks like. So we have this. This is the entire query. And this line over here just enables logging for the query. This is the select clause, and I'll explain this in a while later, but basically select these columns from this table. This table is this initialized from this. You can see it's this constructor over here. So from this, where your conditions mentioned over here, right? These three conditions here are replicated here, and limit fetch. So does it guarantee that your columns exist? Because these are now like Go code. If you accidentally typo something, you throw a compiler error saying this doesn't exist. So that's good. Does it guarantee that you use the right operations on the right column? So you can see here, just now I did name not equals to user ID. Can I do it here? Nope, it's another compile time error, because if you look at the signature for this function, it actually takes in a string field and it expects a string field. And what's user ID? User ID is a number field. So it's just a very simple function mismatch. And does it guarantee that you map the columns to the right data type? So you can see here, this selection is actually, you'll notice that these are the actual columns. So how you can interpret this is, basically I want this column as an integer. I want to assign it to the user ID here, which is an integer, right? So basically I want all these columns. If I do something like this, wrong data type again, because row.int expects a number field and name is a string field. It's a string field. So you can't put the wrong data type inside these functions. And it also guarantees that you map the columns in the right order, because it doesn't actually matter what order you put these statements in. So you can mess them right up. As long as email is always mapped to email, you always get the correct mapping. You won't map email to name accidentally. I mean, you visually inspect, you see email, right? Name and name. So it guarantees that you do it in the right order. Okay, yep. So that's the benefit of using SQ. At this point, does anyone have any LT time before? Okay, so I'll just answer the questions right now. Why didn't I use an ORM or framework? Because I mean, it's not really encouraged. You know, like Go has this really do it yourself. Maybe not so, but basically you try to stick as close to you try not to over abstract things. So basically, if your problems can be solved with SQL, and my problems could be solved with SQL, like I didn't find it too difficult to write SQL. You just stick with the simplest way. And is LT time the equivalent of before? So LT time is, oh, okay, sorry. Maybe I'll show. Okay, so basically there's a whole bunch of like comparison operators, which I can show you right here, comparison operator reference. So you've got EQ, which is equals, NE, which is not equals, GT, GE, LT, LE, right? So all these are like these, but if you, additionally, you may also have a primitive type variant, which only accepts the type. So basically, if you say LT time is less than time, so it has to be less than a time.time value. If you use LT by itself, it expects a time field. So that's how I get around the Golang generics, the lack of generics in Go, right? You have to specify what type you're working with, right? After. Less than time. I mean, less than time would be before, right? And after, so less than time would be before the time, and then after, GT will be after the particular time argument. Right. Okay. So yeah. So basically, this is the general syntax is you select a bunch of columns, you assign them immediately to a data type, and then after that, this function right here is basically I'll just show it side by side just to give a better example. So basically, over here you scan and you accumulate. This is the accumulation function. So for each row, you map this column to this data type, this column to this data type. And after everything is mapped, you call the accumulator function, which is just like this, right? For each row, you scan and then you accumulate. So this is you scan it in this function, you map it in this function, and you accumulate the results. And after that, you just check the errors and then it's done. Okay. Right. So moving on to the second example. Boilerplate. So the typical boilerplate, SQL boilerplate is you select a column C in a query string, right? Then you execute the query with the prepared statement parameters, fetch rows, map columns, accumulate results. Okay, it's all repetitive, unavoidable code, and you know, ORMs aren't perfect, but they make CRUD so painless though. And how SQL eliminates boilerplate is the idea of selection is mapping. So whenever you select a column, it is already mapped. The result is that all you have to do is you write the query and then you execute it and then you're done. So you can see in the example right here, actually, previously over here, right? So you see here, when you select a column, you can immediately map it into a variable and then you just write the query, right? You just write the query, you check for errors, and then you're done. After this line, you print the users and it comes out. Whereas in a normal way, you have to prepare the query, execute with params, scan, accumulate, check error like here, here, and here, and then after that, you're done. So this is all, the boilerplate's gone. But what's better is that this mapping function here, right? This thing you see right here is a function, and functions are reusable. So let's talk about it in terms of this scenario. What happens if you add a new column to a table, let's say during a migration, and you also have to upgrade the corresponding struct field, right? So in vanilla, you have to update every single SQL query that you run with the extra column, whereas in SQ, just update the mapper function. And I'll show you the example here in X2. Okay, so in this example, we actually have three queries, right? So basically, they're all the same except for the condition that you're selecting from. So you basically select a bunch of stuff from users where get all users whose names start with A. Scenario 2 is get all users whose user ID are the first 10 even numbers. And the scenario 3 is get all users whose name, email, tuple are in this particular list, right? So it has to be this and this, or this and this, or this and this. Okay, so this is three queries, and all of them select exactly the same thing. User ID, name, email, created at, right? User ID, name, email, created at. And now I'll add a new column. So I have prepared one right here. Let's say I'm going to add a profile picture to the users table. And now I will also have to update my database. So I think file goes to SQL run. And I have to regenerate the definitions. So for tables, if you check tables.go, you notice that the profile picture field has now been regenerated by this function right here. And so now I will also have to update the user struct definition. So down here, I'll add profile picture, which is a string. It's a link. It's a string. All right. Okay. So now, before I run it, I'll just run the second example without any changes to the code first. See that I have profile picture as an empty string because I haven't done anything to handle it yet. And now I will have to user ID, right? I have to add this column to every single query that requires a list of users, because you want every single aspect of the user, right? And not just that, you also have to update the scan list. So now I have to also update and user.profile picture and second query as well, and the third query as well. All right, now let's run it again. And now you can see the, oh, that's kind of, did I do something? Oh my God, I wrote user ID. Give me a sec. Give me a sec. Profile picture. All right. All right. Okay. Now I get profile picture. I get a link. Okay. So yeah. So this is it. And now let's look at what the SQ does. All right. So if you take a look at this, it's exact same 3 scenarios, except this time you'll notice that what used to be, let's say, let's take a look at X1 SQ. Okay, so what used to be this function here is, remember, it's a function, a mapper function followed by a accumulator function. Down here, this is the mapper function. It's a name function right now, and now you've got an accumulator function. Let's take a look at what the mapper function is like. It's exactly the same code here. So basically, you just refactor it out into its own function. And now, because I have this in its own function, I can use it in every single query. So every single query, I'm invoking this particular function here, and this particular function here as well. So what happens if I want to update oops. Yep. So this is the function. What happens if I want to add a profile picture? I just have to do user.profile picture equals to row.string, and then this is the argument here, right? I'm passing a reference to a table so that I can call the columns on it. Profile picture. All right. So now I'm mapping the profile picture column to this struct, just one line. And then if I run this, the SQ version, you'll notice that it updates as well, right? So this, and I'll just show you the log as well. So basically, all of these queries have been enabling the log. Yep, I've been enabling the log, so with default log, just so that you can see what the log looks like. It looks like this, basically. Executing query, it'll show you the raw query with the placeholder arguments, followed by the arguments. With bind values, it will now interpolate those arguments in, so you can actually copy this query. You can copy this query and run it inside your, oh shit. You can run it inside. So I'll have to change it a little. Yep, so you can run it inside and it'll give you the exact same data that your application will be getting. And then it'll show the first 5 results. So basically, that's what the log does. And yeah, so by enabling that one line, you will see that profile picture is now in every single query. Every single query that I run has this profile picture column inside as well. And if I take that away, so if I go to example 2 and I comment this out, I run the query again, is that now it's all empty. So just this one line can control the selection columns for 3 different queries because they all use the same mapper function. Okay. Yes, so now this is end of example 2. Let's take a look at the questions. Do I have any experience with Buffalo? I don't have any experience with Buffalo. I actually, honestly, I kind of get the feeling like Buffalo is kind of anti-pattern. It's like, I mean, no offense to the creator, because he's a pretty big Go fan as well. But he came from Rails, and Buffalo was his attempt to recreate Rails inside Go, which is a lot of, how you say, magic. Maybe not so much magic, but basically it's a lot of batteries included stuff. I don't know how to say it. Okay, I don't have any experience in it, so I can't say it, but I prefer to do things the simple way. Like if I can run SQL, I won't want to abstracted away. If I can choose my own router, I will choose my own router, that sort of thing. Oh, okay. Yes. I think my other message got dropped. Have you able to XO command line tool? Yeah, if I'm not wrong, it generates the it's a templating, it's sort of like a templating language, right? So it generates definitions from your, so idiomatic Go. Right, okay, yes. So it generates code, but the only difference is like it's still SQL strings, right? Like, yeah, in this case, it's more like more structured. You've got actual column types that you can refer to, whereas this is you generate the strings and you don't touch them, because if you touch them, you might mess a typo up or something. So that's like slightly different, but yeah, I've seen XO before. I didn't really choose it because at that time I was still not very experienced in anything, so I just went with like everything database SQL. So does SQL with views, temporary views? That's right. It does work with views. So I don't know what a temporary view is. I don't think I've never used a temporary view, but it definitely uses views. It definitely generates definitions for views as well, because I use views quite heavily, and that's a good thing, because views, you can write views for your current tables, and then you generate type-safe definitions for those views, and now you can use them everywhere in your code base as well. It's great. All right. Okay. So example 3 is about handling nested structs and nulls. So what did I write here? Okay, so previously you saw the database schema here, and now I've written all the domain structs that map to each table. So you've got users, you've got teams, assignment, and submissions. And yeah, so you'll notice that users is kind of sparse. I actually left out created data at, but I don't think it's important right now. Like it's an oversight, but it's not really important for this example. Okay, so team struct. You'll notice that although I have a team ID here, I did not have a team ID here because it's a different way of nesting them. Instead, because I said before, a team will have multiple users. So now a team has multiple users, and in this case, it's up to 2 users, right? And then instead of having, so it will just contain a reference to a user instead of the user containing a reference to a team ID. And then assignment is here and here, and this is the nested way. Like, just to give a better overview, this is how everything builds up. So every submission nests assignment, team, and users in this particular way. So a submission has an assignment, a team, and each team has 2 users. That's how it is. That's how nested it is. So handling nested structs in Go, if you're using the database SQL, nested structs require a lot of code to fill in all their fields. Just look at all these fields over here. Right, it bloats your query, and code is very error prone because you have to write a lot of opaque strings, and code that you write for handling these nested struct mapping is not reusable. So how SQ handles nested structs is, you've already seen the concept of a mapper function, where it's a function responsible for mapping a column into a particular struct field. So you don't have to write mapper code to handle child structs, because child structs themselves have mapper functions. So what it means is submission only has to handle this, this, and this. To map assignment, it just calls assignments mapper function. To map team, it calls teams mapper function, which in turn calls users mapper function for user 1 and user 2. So you reuse code this way. And now for handling nulls, there are 2 ways of handling nulls. If you try to scan like a null data into a primitive type, you get a error, you get a runtime error. So if you want to handle it without errors, you either have to scan it into a pointer, such as a pointer to a string, or you have to use a null struct such as sql.nullString. So the downside of pointers is that you can't dereference them in HTML templates. So if you're using them, you gotta find some other way. Or you have this option too, which is this, but it pollutes your domain structures for implementation detail, which is sql.nullString. Like, imagine if you're returning an API, a JSON response to some JavaScript front end, and then they're gonna see your payload like there's, instead of a nice string, you have a object with a valid field and a string field, and they'll be like so confused because this is a Go only thing. And it's unpleasant to constantly deal with sql.nullString repeatedly instead of just a primitive string itself. So how SQ handles nulls is, nulls are converted to 0 values implicitly, but you can still check for the nullness separately in a separate function call. So let's take a look at what that means in an example. All right, so this is what I meant by very bloated and ugly. This is a query. this ugly query basically pulls in every single table that I mentioned over here. It joins all these tables together. And it joins the users table twice because there are two users. So I'm doing a self join and then I'm doing extra filter so that these two users are different. And then I'm pulling all these columns in. And then after that, I also have to scan it in the right order. So maybe I'll just show the, so I've got submission ID here, here. Again, it has to be in the same order, otherwise I get a runtime error. And what is more important is that in this case, you'll notice that this is a left join. So a team can be null, a user 1 can be null, user 2 can be null. What am I going to do? I'm going to have to use like these things here. I'm going to have to generate a lot of temporary variables, because if you look at the definition of a a submission down here, you notice that I'm using all primitive types. So I have to instantiate a lot of intermediate SQL null structs, null ints, null strings to handle the possible null values, scan them in right here, and then I check for error. And after that, I transfer the data over to the actual domain struct itself. So this is really error prone. Like I'm introducing so many local variables in the scope. I could just mistype one of them. Like I've got user 1, user 2. What if I accidentally wrote this instead? Yeah, it's very dangerous. So that's that, and it's also very boilerplate heavy because of the whole null handling thing that requires all these variables here. So now take a look at what SQ is. It's very short. Well, relatively short. It's 42 lines. Okay, so in this case, I'm pulling in a lot of tables, instantiating the submissions, assignments, teams, users table. I'm instantiating two of them, right? You notice it's users as U1 and users as U2, and I'm assigning them to two different tables here. I'm doing a bunch of joins, order by, but the most important thing is this selecting, which is like super compact. And that's because if you look at the mapper function, it's a mapper function that takes in like 5 tables. So this submission ID is mapped to this submission ID here, and then when I hit assignment, I just call the assignments row mapper function, the mapper function here. Scan into is like a generic version of scan. So for scan into, sometimes you have different database values that implement the driver.scanner or something like that, the interface. So for those types, in this case, answers is actually a JSON field, and this is a JSON column. So I don't actually have a row.json function. I don't have a row.json. So the only way to get around it is to just directly do a scan this column into this, the address of this variable. So that's what scan into is, right? Team will call the team's row mapper because it's a nested struct. And then if you chase the mapper functions, the team mapper function again calls user 1's mapper function, and it passes the user 1 table in. And then for the user 2, it calls user 2's mapper function, and it passes the second user table in. And then you notice that I'm using this code written here twice. So just like that, mapper functions calling mapper functions, I can just call a mapper function at the top level. I don't have to care what columns they're selecting, because they'll take care of what columns they're selecting and what variables they're selecting into. It'll populate this submission struct accordingly. And then for the accumulator function, after each mapping iteration, I just append it to this submission slice, and I'm done. Right? Yes, and also you'll notice that the whole thing about null values is avoided, but let me tell you how you want to check. Let's say if you actually want to check whether it was null or not. So maybe you want to do something like this, right? Bool. This is actually a flag to check whether the entire team is valid or not. Like maybe if this is all null fields, this will be not valid. How you check is just check whether the team ID is null or not. Because if you think about it, if the team ID is non-existent, everything down here will be null as well. And it's very simple to add on. You just do valid equals to row dot int valid. Int valid is the corresponding function that checks whether this integer value is a valid column, and then I'll just t.team ID. So just like that, I can check. Basically, this will return, if you look at the definition, int valid returns a bool value indicating if the number field that you pass in is non-null. So that's how you check whether it's actually null or not. But otherwise, if you don't need to really know whether it's null or not, you can just implicitly convert null values into 0 values. So if this was null, this will get assigned 0. So that's it. Okay, so question, any specific reason to, okay, so any specific reason I've not tried to make the generated names more Go idiomatic? That's interesting because I also have an example over here. Right, the reason for all caps, right? So The reason for all caps is Juke does it. This is actually a huge inspiration. If you know Juke, it's a Java query builder library, SQL builder. It's exactly the same thing. So basically, see, Java also uses Go's, not quite mixed caps, but it also has it doesn't use underscores. But in this case, Juke decided to go with these all caps for the names, the column names. So it's like, okay, fine, I'll just copy them. Second reason is it's SQL. It's not Go, so it's fine if it doesn't follow Go convention. So these are the two things, right? Go requires exported fields to be capitalized, and SQL is case insensitive, so it uses underscores as word delimiters. So all caps is like a combination of the two. So it's both capitalized and it's delimited by underscores. So you don't have to do any sort of underscore to mixed cap translation. You literally just uppercase everything and lowercase everything if you want to translate between SQL and Go. Yeah, and it's also easier to read because like the table and column names visually stand out from your application code. In the case of, you see here, I've got team ID mentioned here 2 times, but you know this is a column and this is an actual int because of the naming convention. Okay, yeah. So that's example 3. Example 4 is about programmatically building queries. For something called the structured query language, working with SQL in Go is actually quite unstructured because the only way to interact with the database is by sending opaque strings to a database. There's no protocol for sending more structured objects. And in the scenario, what happens if you want to query data based on user input? So I have this code here. So this is simulating user input. So let's just pretend that these variables you see right here are something that you got from the user, something that user input manually at runtime. Okay, so I want to select a bunch of users, and depending on whether the values passed in was zero values or not. So basically I'm saying if the user passed an empty string, it means he doesn't want to filter anything by string. But if he passes in something, it means he wants to look for a user, a name who contains this string over here. So if you're familiar with Postgres's SQL's wildcard operator, it means this percentage means it can be any character, any amount of times. So basically, I'm just saying I want a word that contains the letters E and S inside, and then I want an email that contains this string inside. And so I have this selecting, and then now I'm going to check. Okay, did he pass in a name? And if he did, I will pass this in. I'll append this into a list of predicates, and I'll append the argument inside as well. And then email, did he pass it in? If he did, append this u.email I like into this predicates as well. Created that. So did he provide any values at all? Is it a 0 value? If it's not 0 value, then I'll say, okay, I want to create that between the start and the end values. And at the end of that, I'll just generate a query with the predicates, and they're all joined together by the AND operator. And because I'm using Postgres, which has this quite inconvenient syntax of placeholders that require you to use numbers. So you can't just use the MySQL's question mark, question mark, question mark. You have to use like $1, $2, $3. I have to run an extra code to convert all these question marks because I can't use dollars here, man. I don't know whether this is actually $1 or $2 because that will depend on what happens up here as well. So I use all dollars down here, and then at the bottom I rebind all of these question marks into the actual dollar symbols. And if I run the query for vanilla, you can see the query right here. Yep, you can see it works as usual. So I like this, like 2 between 3 and 4, and then you've got these arguments at the bottom here. So this is a lot of string building. It's not something you want to put in your business logic. Like it's not something you want to concern yourself with, and that's what SQ lets you do. So you've still got these things: simulate user input. Now you just instantiate a table. You start with this query, select these columns from this table, and then you check the name. Did he pass in a value? If he did, just add where this. Then email, did he pass it in? If he did, then where email I like this particular string. I like this string. And then after created add is if he passed in non-zero time values, then after again between this time start and time end. And then you just have to run to SQL to get the query and the args, and then you can print them out. So if you just run it this time, you get exactly the same thing. Let's compare it. vanilla and SQ, and you can see that they're exactly the same arguments, except this one you didn't have to concern yourself with string building because it's all handled by the query builder library. Why am I using printf's funcs without parameters? What? Printf? Oh, you're right. I'm sorry, man. That's I thought I was gonna put I thought I was gonna interpolate actual values inside. Then I realized no, it's a prepared statement. You're not supposed to interpolate anything. So I forgot to leave that out. Yeah. So that's a pure mistake. It's supposed to be something like this. Yes, that's right. There are more available SQL features supported by this library, which I'm not going to go through. You can check out the links in the top. Basically, it supports upserts for both. This is for Postgres, insert on a conflict, and MySQL, insert on duplicate key. There's update, delete with joins. So you can join tables in your update and delete queries. There's subqueries, common table expressions, row value expressions, case, union, intersect, except. You can generate Typesafe definitions for your PL, PGL, SQL functions as well, which I also use. Like I wrote a bunch of PL, PGL, SQL functions, and I generated so that I can call in Typesafe from my Go code. And you can also interface with the array type from native Go slices, which I think you also saw in example 2. Let's go over here. You can see here I have a list of even numbers, and what I'm actually doing is in a slice of even numbers, and it converts into this is not actually Go array type, but well, basically there's support for slices. You can pass in slices into this, and it will just convert to the corresponding arguments as you would expect. So in conclusion, why is SQ? Number one is you get compile time guarantees about your queries. Like you get existence checks and data type checks that you you mention columns that actually exist in your table, and you ran all the right operations on each column. You eliminate the boilerplate with the concept of selection is mapping. So whenever you select a column, you automatically assign it to a variable. So you don't have to do anything after that. It eliminates boilerplates when it comes to scanning data into nested structs and nulls because of the implicit conversion and the mapper functions. And lastly, it's a query builder, so you can programmatically build queries. And bonus is it's easy to adopt in code bases because it's a glorified string builder. So if you have a code base with a bunch of like raw SQL queries, you could upgrade a couple of them, just a select few, to use SQ if you want some type safety or if you want to eliminate boilerplate. And then you just have to generate the table definitions, and then you're good to go. You can use them. No other queries in your code base has to know about the existence of SQ query builder. So that's the end of my presentation. And let me just look at the examples again. The comments. Golang, yeah. Man, this is like a super throwaway sort of thing. So technically, I should be running a linter, but and it would have caught that. But in this case, a very, very raw sort of thing. So I didn't run a linter for this.
How long do you take to do this?
The holiday law. During the past holiday, right after the previous semester ended.
Okay.
Yeah.
Nice. Are you going to be actively maintaining this?
Yeah, man. I feel pretty passionate about the SQL, writing SQL. So
okay.
I feel like there should be a better way to write SQL and Go. Have you tried it? Oh, dude. Yo, I love the generics proposal. All right, so you saw the there's so much things I could do if there were generics. Like there's this comparison operator you saw already, right? I have to use like EQ that accepts fields, EQ in accepts in, and Juke you don't have that, man. In Juke all you have to do is EQ, and this EQ handles like everything you throw at it. It's still type safe, it's still integer floats or whatever. But if I have generics, I can do like EQ that accepts multiple types, like a sort of like a union type, I think they're called. And then when I'm scanning, so for example, this it's a scan into. I had a scan into, right? Yes. There we go. So let's say I have JSON. First I have to do this because row.int is a function that yields an integer, but I have to use this more clunky way of scanning into the address because I don't know what data type it should yield. So this one, it should yield an integer. It's scanned into, it doesn't yield anything because it scans directly into address. If the preferred way is probably, I think it would be like scan, maybe like JSON or something, you know, like pass in a type argument, and then after that, like a.questions, and then after that, sign.questions. I mean, JSON is not actually a type, but basically whatever type you pass in will be the values yielded by this. And then that's more like syntactic sugar for the library, which is going to be great when it comes out.